Baxley, and I'm the Chief Engineer of the Ocean Energy Program at Florida Atlantic University down in Boca Raton, Florida. Please note it's engineer, so I look at things of the effects that science are going to have on the devices that I'm trying to build. So even though I like to understand the fundamentals behind why these things are happening, to me I'm trying to bound the problem so that whatever I build is not going to break if I put it out there, okay? So just really quickly, we are one of 3 DoD ocean energy sites. There's one up in Oregon. They're doing mostly waves and tides. Out in Hawaii, we're doing waves and OTEC. And then down in South Florida, we're doing ocean currents. And even though it says OTEC, it's not necessarily OTEC. It's more like cold water air conditioning, that sort of thing, where we're not doing any energy transfer, but we're reducing energy requirements through that sort of technology. So just really quickly, while we're doing ocean currents, the 3 fastest currents are also close to the major load centers in Europe. In Japan, there's the Kuroshio by Tokyo, obviously. Southeast US, Miami, Fort Lauderdale area. And then in South Africa, those are the 3 main areas that they're looking at using these ocean currents for developing energy. So this is just a cross-section of the Gulf Stream at 26 degrees latitude, which is off of Port Everglades. And what it shows, it's the western boundary current, so it's intensified to the west. And we have the highest velocities over on this side of the Florida Straits. And it's also up closer to the surface, right? So that's challenging from a deployment perspective. And the extractable potential, we're looking at about 5 gigawatts. Even though there's between 15 and 20 gigawatts of energy out there, nobody's that good, right? So we're kind of balancing. We're toning it down a little bit so that 5 gigawatts is hopefully what we'll eventually get to achieve. And this is just an annual profile of the velocities. And obviously, you see in the summer it's higher velocities, thermal handling circulation. So the warmer the water, the faster it flows out here. And then, but it also shows that obviously the currents are closer to the surface. Down near the seafloor, they're quite low. Now, one of the things about, okay, so what's the historic, the consistency of the current? And so I thought this was kind of cool. So we have these 3 profiles here. One was taken in '84 during the STAX experiment. There's probably a lot of you guys are very familiar with that. I was in high school. This was 2005 when University of Miami had a cruise ship going back and forth between the Bahamas and Miami, and they generated this profile. And then this was in 1889, actually published in 1890 by Lieutenant Pillsbury. He took his vessel and moored it at various places directly in the Gulf Stream for months at a time, and he made this profile as well, which was really cool. It's a really, really cool story if you ever read about it. I mean, if you've ever been working out in the Gulf Stream on a modern DP vessel, and you have all the safety stuff involved, and you imagine some guys out there moored up with hemp rope down in 1,000 feet of water and 5 knots of current. It's just amazing. So anyway, so to me, obviously, it's not down to the centimeter per second, but at least it shows that the trend is consistent, right? At least it just works. Because everybody always asks me, well, is global warming going to slow down? I have no idea. But for the last 100 years, it looks fairly consistent. So again, engineer perspective versus scientist. All right, so open energy approaches. So we had a couple people talk about tidal energy, and one of the advantages there is you can mount it on the bottom, right? Because it's fairly shallow water. So not the case out where we are. And so these are several different approaches from different companies. This is ocean current energy, where they have a whole farm of devices up in the water column. This is our prototype turbine that we developed at FAU a few years ago. This is a Qantas, where they have 2 counter-rotating blades. And this is Anadarko, where they have, it's more like a helical tube that turns and makes electricity based on the flow. So, open ocean MHK. So what are the challenges? Okay, so it's in deep water, right? It's in 400 to 500 meters of water, at least in our area. Off of Japan, it can be in thousands of meters of water. So that's quite a challenge over there. Distance from shore, we're between probably 20 to 30 kilometers offshore. Continual high flows. So we don't get a slack tide like you do in tidal. So, we always have to deal with the high currents. They may change a little bit, but it's on the order of weeks to months that they really change significantly. but they're pretty much always there, except during hurricanes, which I'll talk about. The prime flow is near the surface, so if you're in 400 meters of water, that upper 100 meters is where you gotta be, right? So that's 300 meters of nothingness that you have to deal with. So that's kind of cool. And then tropical storms, right? Tropical storms, always a bad thing. So what are the advantages? Well, the advantages are we're in deep water, right? So we have a lot of room to work with. Kind of like landing an airplane, right? It's only really scary, right, when you get close to the ground. When you're up in the air, you got time to deal with problems, right? So we have a lot of water column to deal with. The distance from shore, you know, nobody can see what you're doing and screwing up. No, not really. So the distance from shore, at least you don't have a lot of small boat traffic and that sort of stuff that could interfere. And a lot of the shipping traffic tends to be inside. Continuous high flow, so you're consistent, right? So you don't have to worry about it changing on you during the day. The prime flows near the surface, okay, well, that gives you some advantages that I'll talk about. But tropical storms suck at any time. So tropical storms are not cool. And then just a few other things before I get off of the actual devices. The transport and deployment of these large systems, because again, you have to put it in 5 knots of current when you're standing still, so that's a big deal. Control systems, large device hydrodynamics, some of these things are tens of meters in size, so that's a lot of drag in 5 knots of current. Complex and unique moorings, you gotta hold them in place. Power transmission, how do you get all this power back to shore over 20 kilometers? You just don't want to put an individual turbine on one mooring in 400 meters of water, so you have to integrate multiple devices. How do you work on it? Because again, you don't get slack tides, you can't send divers down, it's a couple hundred meters deep. Pretty interesting. And then vessel traffic, because it's right in South Florida where you have Port Miami, Port Everglades, West Palm, all these other places. And this is just a really quick little nightmare scenario of all the forces that would act on the device here in the center. So you have a variable velocity, so you have a lot of vertical shear. You have to stay below 50 meters for a variety of reasons, because you have deep tow tugboats coming by, you have Navy submarines in the area, and also a lot of other vessel stuff. So you've got operating range between 50 to 150 meters. You have to go hide sometimes, which I'll show you, down to 200 meters when storms come by. And then you have the drag on the cable, all the moorings, the water depth, all these other type of forces, right? So got all that stuff against us. But the purpose of this talk is the weather and the environment itself, right? Because again, I need to bound the problem of how we're going to design all this stuff. So SNMREC, the Southeast National Marine Renewable Energy Center, the 2014 worst acronym on the planet award. SNMREC, so I just call it our Ocean Energy Program. So these are some of our systems. This is where we grow our ADCPs. These are almost ready for harvesting. And we started off using the flotation technology, which is now deep water. We started using those, but since we're only in 400 meters of water, there's no reason to use a 1,500 meter rated, very heavy, very large buoy. So we also started making these smaller, lightweight systems on our own, just to help with recovery and everything. So we typically go out and put 4 in at a time. We did have one break away around 2010. Just for the record, I didn't start with them until 2012. But I did get a trip to the Azores out of it. So anyway, so it broke away. A couple years later, we get a call from the Azores. I go over there. And of course, the one that was lost had not only a long ranger, but it had a workhorse 300. It had a Benthos acoustic modem. It had CTV. It had everything we could put on it. And that's the one that broke away. So it was very important for me to go over there and take all these parts and pieces. And the University of Azores got a nice 48-inch buoy. The similar metals, for anybody that ever deployed anything, you gotta be careful. You gotta make sure, it might be nice and shiny before you put it in the water, but it might not be stainless, right? So this was probably the thing that happened. And then we have some CODAR systems down there, about a 30-mile separation down. One's in Hollover, just north of Miami, and one just north of Fort Lauderdale and Hillsborough. So, when we were getting all this data, we also do a lot of public speaking, and it's kind of hard to show those year-long profiles for the lay people to kind of get a feel for how the currents actually behave. So I wrote this code, and I gave a paper on this a few years ago, on just taking ADCP data and animating it in time, synchronizing all these different ADCPs, which are essentially independent measurements, and you can kind of see, except for those outliers, you can kind of see how the whole flow is working, right? It's all working top to bottom. You see that there's less flow down at the bottom. And you can see how it varies at the top. And we also have our, actually, I'm sick, sorry. And then we also have the CODAR data here that, that shows the flows and some of the variations and stuff. But what I found, when I make totals out of my CODAR data, it looks really cool like that. They swirl all over the place. When I get help from the CODAR people, they're all nice and boring and straight, so I don't know. The other thing is you can use my same software for doing title if you want to visualize or to explain to somebody how the top to bottom velocities in a current. This is from Fort Pierce Inlet because we were doing some work there as well. So, what's the main thing we need to worry about environmentally? My button push. Hurricanes, right? Death and taxes and hurricanes. It's going to get you if you're in this area. So we really need to see, okay, so we've measured the current since 2008. What happens when a hurricane comes by? So we have Hurricane Sandy here. If you notice, it stayed off to the east of us. It's about 500 kilometers was its CPA, or closest point of approach. So our CODAR during Sandy, it showed some really, a really strong eddy right here up near our Hillsborough site. Went out there a couple days later, and that was the effect of it, right? It completely washed away 200 feet of beach, took our CODAR sites with it. And so we lost one of them. Fortunately, we got some funding back, re-ruggedized everything, and I designed it for 116 miles an hour as far as drag, and it fails with grace, or like in Toy Story, right? Falling with style. So it doesn't break, it bends, right? So it just, the mooring will fail, not the mooring, the anchor will fail, it'll just lay over. So we can come back and set back up instead of it breaking off and stuff. So anyway, put up a new weather station because that was an important thing as well. We recognize that. So this is during Sandy. So what's really cool is the wind's blowing to the west, and so it tends to be speeding up. But then as soon as the wind switches around, you see that in the upper 150 meters, it really affects the top of both of them, right? It really backs that up, whereas down here in the core, it just keeps going to the north. And this here is the difference in predicted and actual tide down in Miami. So not only does it slow the surface velocity, but it backs up the flow to the south as well. This is from the top. And so these are the two out in 340 and 260 meters of water. These are in 130 meters of water. So see, they're spinning like tops, right? Whereas out in deeper water, they're changing in velocity in magnitude, but their direction is still going to the north. That's very important because the closer you get in, as I think one of the speakers said, with the longshore drift, you get some really weird rotations in the shallow water, right? And I'll talk about that here in a second. The other cool thing is, since it's in this code, I can do a progressive vector diagram and show all these rotations for the shallow ADCP, just how many times that the velocity is changing in that shallow water as a hurricane. So now let's see. And then this is the plot. This is when the storm was there. You can see the higher velocities. But then 10 days later, it all goes to zero essentially, right? The Gulf Stream stops. So we've got really high flows, and all of a sudden, boom, it stops. And even in direction, you can see, it still stays pretty much to the north, but there is a little bit of direction change down here about 10 days later. So then Sandy comes along, a couple days before. As it's coming along, we're not quite sure when it's going to make this dog leg. So I want to get an ADCP out there. So I talk this ship in, I take a little ADCP down there. This is the weather on the way back in, calm before the storm. That wasn't the problem. This was the problem, right? I was on this side. I was like in Walking Dead when he's driving into Atlanta, right? I was like, where you're supposed to go. So we went out deployed, and then later that night, I had to get my way back here. That wasn't the worst part. The worst part is my kids were waiting for me up in Fort Pierce. My wife was in Peru. She called my son and said, "Where's your dad?" "Oh, he's out on the boat." Not cool. So anyway. And then this is Irma as it's coming up towards Miami, so you can see all the inflow coming in. So now I've added color. So again, this is Irma now, the velocities, and you can see how high the velocities are when the storm goes by. But then if you look at it from the top, it'll play. So you get the really high velocities going this way, you don't really get a shift, but then it does drop down to 0 again, right? So it always stays to the north, but then it drops faster. This is a picture of the Kodar, where the Kodar, the power went out right when the storm was coming by. So we lost power, but this was like our last clip right before, but it shows this eastern eddy out in the Gulf Stream. And then this was Sandy, so we had Irma. So we had the high flow. 10 days later, we had this drop in flow. So what does that mean, right? Well, Sandy had a really a really dramatic change, but constant wind, whereas Irma was, the direction never stayed constant, so Ekman couldn't really develop, right? And so this is my gratuitous math slide. This one. So the Ekman depth and the velocity, and so at 8.75 meters per second at our latitude, the Ekman depth should have been around 100 meters or so. And that's where we were seeing some of that stuff during Sandy, because it had a rate of change of 0.7 degrees an hour, whereas during Irma, it was moving too fast. It was clocking around at 3.2 degrees an hour, and it never had a chance to set up the Ekman zone. So that's what I'm guessing. So those are the differences in water. Some guy told me to look at the change in the Gulf Stream transport during the time. So this is with the start of the storm of Sandy, transport went way down. Starting Irma, transport went way down, whereas through the year, it's all around 32 sphere groups. So, but again, I'm just looking at what's going to happen to my device is where the local velocity goes to 0. So what do we need to do? We need to put ADCPs out every hurricane season before the day before. Put out multiple arrays that can capture the rotation as well as the velocity going forward. A long stream, so I need one probably a couple hundred kilometers either way. So maybe this delay is something that's happening upstream before it gets to us. It's just propagating through. Make sure we got enough power systems to run it. And then there's a lot of other stuff I got time to talk about because I'm at 16 minutes. But anyway, so that's our that's what we learned from hurricanes going by and how I have to design to that as well. So there you go.
Hey, questions?
No? Yes.
Bill, I was in on a lot of these discussions years ago when Bill was working on those projects.
Mm-hmm.
It's more of a political question. How is our new administration in Tallahassee? Are they in support of this work? That's the question.
Well,
Are you getting good feedback from
well, okay, so they are, but not for a specific program. They're working with Lake Worth a lot, because Lake Worth wants to become a blue energy hub in Florida, right? Because they're close to the Gulf Stream. They're only about probably 20 kilometers away. And they have their own municipal power plant, right? So they don't have to play with FPL, that's the state power plant. So they want to become that. And so the governor is really interested in making that like a showcase ocean energy, the new governor in Florida. So that's a good thing. So yeah.
Okay, thank you very much.
Okay, thank you.
Okay, next speaker from